We're reviewing the exam 3, and let's go over the content. I'm actually going to start backwards. So one of the last things that we talked about was factors and divisors and prime decomposition. So I'm going to start with that, and then I'm going to work my way backwards to the first topics, which was the enumeration systems. So starting like, what are the factors and divisors? So the idea is that we're looking for numbers that if you multiply them, they would give you the original number. For example, 6, what are the numbers that would give you 6? And so such numbers would be 3 and 2, 1 and 6. So all of these numbers, 1, 2, 3, and 6, they're called factors or divisors. These two words, they're actually synonyms, but when we think of the word factor, we're thinking of a multiplication. Like this is a number that multiplied by another number will give you 6. And when we think of divisors, we're thinking now on division, like this number fits evenly into 6. So that is the actual definition is on the bottom. It says the natural number A is a divisor or factor of the number B, provided that there exists a natural number J such that A times J equals B. So that this is actually the original definition of multiplication and division and factors and divisors. So other examples are determine the natural number divisors of each number below. So what are the numbers? And then when we talked about naturals, these are numbers starting with 1 because these are numbers, we also call them counting numbers that you can find in nature. So it's like the most intuitive numbers like 1 chair, 2 pencils, 3 notebooks, and so on. So natural numbers start from 1 and consecutive numbers like 2, 3, 4, 5, 6 till infinity. No negatives. So this is why we don't consider negatives when we're doing factorizations. They're not natural numbers. Well, for A, those numbers would be 1, 2, 4, and 8. How would you verify? Well, can you multiply 1 by something and get 8? The answer is 1 times 8 will give you 8. Similarly, 2, can you multiply 2 by something to get 8? Yes, 2 times 4 is 8. So this actually gives you, like, they come in pairs, 2, 1, 2, 4, and 8. For 42, now we have a bigger, because this is a larger number, we have much more factors or divisors. Starting with 1, so every number is divisible by 1 and is divisible by itself. So that would be 1 and 42, but then other numbers would be 2 because 2 times 21 is 42. Another one would be 3 because 3 times 14 actually gives you 42. And the last pair, 6 times 7, also gives you 42. So if we list them all, we have 1, 2, 3, 6, 7, 14, 21, and 42. Notice how there's a jump. Once you get to half of the number, like 21, there's no others. So that's kind of like a simple way of looking for those numbers. And the other, the last one, 17. 17 is actually a very special number because it only has 2 divisors, which is 1 and itself. So these are actually what we call the prime numbers. Prime numbers are numbers that, by definition, they need to have exactly 2 and only 2. For example, the number 1 is not considered a prime because the only natural number that divides it is itself, which is 1, and so it doesn't have 2. So as mentioned, the natural numbers, so we're gonna, because 1 is not considered a natural number, to find primes, we're gonna start with numbers greater than 1 that have exactly 2 factors or divisors, itself and 1. And the numbers that are not prime, we call them composite numbers. And these are numbers also greater than 1, but these are not prime. So if we look at the definition of prime, primes need to have exactly 2 divisors. So the composite numbers, they have more than 2. Like they gotta have more than 2. They need to have 3 divisors, 4 or 5, just more than 2. And one of the exercises is to identify or classify prime or composite numbers. For example, is 100 prime or composite? Well, again, going back to the definition, to be prime, the only divisor has to be 1 and itself. So if you can find another divisor of 100, which is now 1 of itself, then that would make it composite. And in fact, there's too many. Is divisible by 2, is divisible by 4, by 5, by 10. So this clearly has a lot of divisors, which means it's not a prime. The next number, 41. 41, actually, well, this solution, it is not accurate. It's repeating the same ones. But 41 indeed is also a prime because it is not divisible by anything except 1 and 41. So 41 is actually an example of a prime. 51 is actually showing me the same one, I believe. Oh no, it part of it was correct. Like on the top, it said 1 and 41. The factors of 51, 51 is actually divisible by 3. 3 times 17 would give you 51, which means it is composite. And the last one, 119, this is also a composite number because it is actually divisible by 7 and 17, which are different from 1 and 119. So the only prime that we had was actually 41. So the composites were 100, 51, and 119. Next, something that we're interested in doing is find the prime factorization of numbers. Actually, a lot of problems in number theory, they can be solved by factoring numbers. And the most reduced, the unique factorization that a number has is the prime factorization. So the prime factorization is very important when you're solving questions, when you're solving word problems. And the nice thing is that we know we have the fundamental theorem of arithmetic that says that every composite number can be decomposed, you can write it as a unique product of prime numbers. The difference might be perhaps the order of the factors, but it's going to be exactly the same factors. So, for example, 6 is a composite number, and the prime factorization of 6 is 2 times 3, where each one of these is prime. Notice that you could switch it. Maybe you could write it as 3 times 2, but it is exactly the same primes. So that's why we call it unique, except by the order. Another example would be 84, the prime factorization. So one way that you can find the prime numbers is by starting one prime at a time. And I like to start with the smallest. So if you divide it by 2, you get 42. So 2 times 42 is 84. And then now continue decomposing 42. That would be, it's still divisible by 2. So divided by 2 one more time. You get 21. So 2 times 21 is 42. Notice that because these 2's are already prime numbers, 2 is the smallest prime number. So it's already a prime. Then you continue, the ones that I'm decomposing are the larger numbers, like 21. Can I still divide it into smaller numbers? The answer is yes, because 21 is equal to 7 times 3. And then at the end, I look at all of my primes, 2, 2, 7, 3. And this is my prime factorization, because if I multiply them, 2 times 2 times 3 times 7, that gives me 84. and all of these are primes. Usually, a simplification of this is anytime that we have repeated numbers, we put them as an exponent. So since we have two 2's, we write it as 2 squared times 3 times 7. So this is kind of like going again step by step with each of these numbers. Another prime factorization for 495, and you can actually find the prime factorization in different ways. I recommend the left one, which is the one where you do it in order. So I recommend that you go start with the smallest number that you can divide it by. So 495 is not divisible by 2 because it doesn't end on an even number. And then the next number that I would try would be 3. And if you try to divide it by 3, it is divisible by 3 and you get 165. And then I will continue again, like, is this divisible by 3? The answer is yes, so I get a 3. And on the other side, I put the result, 165 divided by 3 is 55. And is this divisible by 3? Well, this is not. And in your calculator, you will probably see like decimals. Like the answer would be probably 18.2 something. So since you have like numbers after the decimal point, it means that it doesn't fit evenly. So try another number. How about 5? And it turns out that it is divisible by 5 and you get 11. So all of these numbers divide evenly, so we never get decimals. If you get decimals, then the number does not divide evenly. And next, you collect all of the different primes that you divided by, starting with the first 3, and then 3, 5, and 11. So this gives you 3 squared times 5 times 11. On the other hand, if you had started dividing by 5, of course, it is divisible by 5 because we already had it before. And so you get 11, you get 99, and then you divide 99 by 11, and that gives you 9. And then you can decompose 9 as 3 times 3. And if you notice, this is exactly the same prime factors, but in a different order. Now I started with 5, then 11, and then 3 and 3 at the end, which is exactly the same ones that I had before, but just in a different order. So technically, we count it as the same. Okay, so that was like a short review of prime numbers and how to do the prime factorization. One of the topics that we cover a lot was the different numeration systems, starting with the ancient numeration systems. And this is very helpful because understanding how different numeration systems actually helps you understand how do we do the operations the way that we do. I always say that if you analyze, for example, multiplication of 2 digits times 2 digits, or a division like the long division, you realize that there's a lot of rules that they don't seem to make sense, and it all comes from like I mentioned, by studying different numeration systems, it helps you understand why we do things the way that we do. So in this example, we have a number, or as is better called a numeral in Egyptian, and we want to write it in a typical number that we recognize, which we call Hindu Arabic numbers. And to answer this, all you need to know is the conversion table, which you see on my screen. And as I noticed, I started by noticing that the pointing finger is 10,000, and I have 6 of those. 1, 2, 3, 4, 5, 6. So I multiply 6 times 10,000, which is 60,000. Then I look at the lotus flower, and I have 5 of those. That's going to be equivalent to 5,000. Then I count, there's 7 scrolls, each one 100. So those 7 are going to contribute 700. I have the heel bone, 6 of those. Each one has a value of 10, so that's 60. And lastly, each of those vertical lines is called stroke. There's 9 of those, so and each one has a value of 1, so that's just 9. So to find what this number represents in Hindu Arabic, I add all of those numbers, 60 plus 5,000 plus 700 plus 60 plus 9, and that gives me 65,795. Since I'm adding all of these different numerals or all of these different symbols, we call the Egyptian system an additive because to find the answers, we gotta add the symbols. Let's do another example. So now I'm gonna do it backwards. If I have a number in Hindu Arabic, can we write it in Egyptian hieroglyphics? And the way that I would start is I would start by decomposing the number. So 23,000, you can write it as 20,000. And then this is the 3 is on the place of the thousands plus 3,000. The 4 is on the place of the hundreds, so plus 400 plus 2. Now, since 10,000 is a pointing finger, then I need 2 to get the 20,000. Since the lotus flower is 1,000, I need 3 to get 3,000. Since I have a 400, I'm going to need 4 of the 100, which is the scroll. So I write 4 scrolls. And I need 2 units. And a unit is one of these strokes. So I need 2 of those. So these hieroglyphics represent the number 23,402. Something very interesting about hieroglyphics is that it doesn't matter, at least numbers. I don't know the writing, like if you're writing a message, but at least when the Egyptians were doing numbers, the order did not matter. So you could put the lotus flowers in any place that you want. You could put them on the left, on the right, in the middle. Any of these symbols can be placed anywhere, and you still get the same answer. Let's do another example. So the next number system is going to be the Roman. And we still nowadays have a lot of like Roman numerals. Like we use them a lot when we're writing a paper or an essay. Or you can still find maybe a watch that uses Roman numerals. And usually the hardest thing is exactly this example. If I give you a Roman numeral, do you know what that represents in regular numbers, in typical numbers? And so to find these, you do need to know, let me go back. You do need to know what each letter represents. So again, now these are actual letters. So this is going to be I represents 1, V is equal to 5, X has a value of 10, L is 50, C is 100, D is 500, and M is 1,000. This is very important, just like the Egyptian numerals or symbols. You do want to have these in tables. If your instructor does not provide you the formulas, or perhaps as you're preparing for the test, a great idea would be to write all of this in a single sheet, like a cheat sheet. Have all of that together so that you can look at it, you can refer to it to solve any question. So I feel like it would be easier if you memorize them, but if you don't, it's okay. Just make sure you write them down. And most likely this will be provided for you during the test. So when reading Roman numeral, you start on the left, it's from left to right. And the rule is that any letter to the right has to be smaller value. If it's greater value, then you subtract it. If it's a smaller value, you add it. For example, starting with the M, that is 1,000. Then I look at the right and I see a C, which is 100. So that means because the C is smaller, I'm going to start by adding 1,000. And then from the C, I move to the right and I have a D, which is a larger value because it is 500. So then this is going to be a subtraction. I'm going to subtract 500 minus 100, which is 400. Next, I have X and L. The X is actually smaller than the L because X has a value of 10 and L has a value of 50. So I'm going to subtract them again. It's going to be 50 minus 10. And then I move to the V, which is 5, and then 1 and 1. So the last two, I'm just going to add them, 5 plus 2. So this is going to give me 1,000 plus 400 plus 40 plus 5 plus 2, which when you add them, that is going to be 1,447. Let's look at the next example. I know I label it as A as well, but that should be B. So example B, in a similar way, start on the left. So you have M, which is 1,000, and then there's another M that is 1,000. So you start by adding those ones. And then there's a D, which is 500. That's fine. But before we added that, let's look at the one on the right. That's a C, which is smaller. So that means we're going to add the 500. When you get to the C, you look at the 1, which is smaller, so that you're going to add the 100. And when you get to the 1 or the I, there's a V. Well, that's actually bigger because 1 is less than 5. So then you're going to subtract those two, 5 minus 1, which is 4. So this number is 2,604 by adding all of them. Okay, so now I'm going to go backwards. How do we write these into Roman numerals? My first number is 1,039. So we could write the 1,000 by including a letter M. And then I also need 30 to get the 39. And we know that 30, I could have, if 1x is 10, I could repeat it 3 times. Now, that's actually a rule. You can only repeat a symbol 3 times. And you can only repeat certain symbols. For example, you can only repeat the I, the X, the C, and the M. The other ones are not allowed to be repeated. So we can only repeat those ones. You could say we can only repeat the ones that are powers of 10, like 10, 100, and 1,000, and 1. So I'm fine by repeating 3 X's. And then to come up with the 9, if I were to choose 5 and then add 4, that would not work because I can only repeat the 1 at the most 3 times. So instead, I need to get the 9 as a subtraction by doing 10 minus 1. So we would put the I first and then the X so that it works as a subtraction. So MXX IX represent 1,039. For the next one, let's do the letter B. In this case, so if you notice in my solution, a good idea is to kind of like expand it by putting zeros. So the 9 would be 900, the 5 would be 50, and the last 9 would be 9. And so now think of ways of writing 900. Well, if you were to use the 500, then you would need 4 C's, but you can only repeat the C 3 times. So instead, you need to get it as a subtraction. How about you do the 1,000 minus the C? So if you do that, that would be CM, which would give you 900. And then 50, we actually have a symbol for 50. We need one L. And the 9, we saw the 9 before IX. So these letters represent the number 959. Okay, another numeration system was the Babylonian. And the Babylonian is actually very close to how we write numbers because they use place values. And we also have, that's what I say, like the 4 is on the place of the thousands, the 5 is on the place of the hundreds. So the Babylonians also have place values, and their base was actually 60. The regular base that we have is 10. The Hindu Arabic numbers, they increase in values of 10. the Babylonians have a base of 60. So they start with 60 to the power 0, which is 1. So that's the place of the so starting now from right to left, that's the place of the ones, and then 60s, and then 60 square, and so on. So to decode this number in Babylonian, it's a good idea to write down a table that has the powers of 60, including or starting with 60 to the power 0, which is the ones. And then on the Babylonian system, there was only like two numerals, the stroke, the vertical stroke, which is the 1, and also kind of like a wedge or an arrow, which means 10. So for example, on the right, I have 12, and then multiply it by its place value, which is 1. On the next place value, I have a 10 and a stroke. So this should actually be 11. Let me see if I can. I don't know if I can change it on the screen, but that should be 11 times 60. And then on the left, I actually have 10 plus 10 plus 1. This is 21, and then multiply by its place value, which is 3,600. Let me see if I have it correct at the end. I don't think this is quite right. It should be 11 times 60, which is 660. And then the other one should be 21 times 3,600. And then at the end, you're supposed to add the 12 that we have in there. And this is going to give you a total of 76,272. So once you multiply each numeral by its place value, you add those numbers, and that gives you the total. I'm going to skip it because I don't know if I don't have the right answer in here. But the answer is 76,272. Okay, well now, what if you want to do it backwards? To do it backwards, also this is kind of like the difficult part because you usually have to do like a lot of work to find it. So if I give you the number, let me see, 7,821, this one, not the one that I have over here. If I give you this number and we want to write it as a Babylonian, what you would do, and you could do this for any base, identify the highest power that would divide. Well, if we look at the powers of 60, we have 1, 60, 3,600, and 216,000. Well, that's too big. So the first number that actually fits into it is 3,600. If you could do this in your calculator, if you divide it, you get the answer is 2, but you may get like 2 point and a bunch of decimals. And so just keep the 2 on top and then multiply 3,600 times 2, which is 7,200, and then subtract, and that gives you 621. So next, get the remainder, that's the 621, and divide it by the next base, which would be just 60 to the power, the next place value to the right, which is 60. And again, how many times the 60 fits into 621? That is 10. The multiply and subtract, so the remainder is 21, and continue dividing until you get to 1. So I'm going to do one more division, which is 21 divided by 1. That, of course, that fits 21 times. And then you get 0. So basically you stop once you get to the 0, once you have already divided by the last one, which is 1. And the answer is going to be created by using the numbers on the top of the long division. So our quotients, the 2, the 10, and the 21. And so 2, we can write it with 2 vertical strokes. At 10, that would be a wedge. And 21, that would be 2 wedges and 1 stroke. notice that we kind of like leave a space in between them to differentiate that this is on the place of the 3600s. This is the 10 is on the place of the 60s, and the 21 is on the place of the ones. Okay, so that's how we write it in Babylonian. Now, another numeration system was the Mayan. The Mayans actually, their numbers were organized from the bottom to the top. So the smallest power is on the bottom, the smallest place value, and then we have in the middle like 4 dots, and then we have the shell symbol. It looks like a shell, and then we have on the top. Now, the first thing that we need to know is the place values, huh? And also kind of like a quick review. So the shell, I'm going to start on the bottom right corner where the symbols are. The shell or conch symbol represents 0. And then we have like the dots. We have 1, 2, 3, 4. And then to represent 5, we have a line. And then we put dots on top for 6, 7, 8, 9. And then 2 lines, that's a 10. And then go on like that, 14. And then 3 lines is 15, and then put dots on top to represent 19. And we stop there because then it goes on onto the next place value, which is 20. So now going on the top right, looking at the place values. So as I mentioned, the ones is gonna be on the bottom, the 20s is gonna be on the next level. And then the Mayans actually incorporated multiplication by 18. And I mentioned before that the reason for that is because they wanted to get the 365, because they realized they were very astrological, and they noticed that 360 was closer to the full rotation of the Earth. So even though they have powers of 20, they start multiplying them by 18. So you get 360, and then 18 times 20 squared, which is 7,200, and 18 times 20 cubed, which is 144,000. And to decipher this number, then I start on the bottom. I have a 12 in the place of the 1, so multiply it by 1. And then these 4 dots represents 4. Multiply it by the next place value, which is 20. I have a 0. This is on the place of the 360, so multiply it by 360, which is 18 times 20. And then there's another place value on the top, which is 2. Multiply it by 7,200. And these, if you add all of these numbers, this actually becomes 14,492. So these symbols represent the number 14,492. Now, we also cover in this section numeration systems. We talked about numbers in different bases. So typically we have numbers in base 10, but you can have numbers in base 5, base 3, base 4, base 16. And so in these examples, I have numbers. I cannot read it as 1,332 because that would be if the number was in base 10. But we see like it mentions that it is on base 4, like an index or a subscript that is telling me that the number is in base 4. So I usually just read it digit by digit. Like this would be 1332 in base 4. So what is that equivalent as a regular number? Well, if it's base 4, the number to the furthest right, the most right value, which is the 2, that would be in the place of the 1s. And then the next value, the 3, is in the place of the 4s. And then the next 3 is on the place of 400. And the last one is on the place of 4 cube. I'm sorry, 4 square and 4 cube. So what I would do, often a simpler way on the book, it's very common that they write down the base in letters, but it's a little bit easier if you just put a smaller value that says that it's base 4. And so you just gotta multiply each of these digits by the place value where they're located, and then add all of those. And 4 cube, when you're doing this, if you're doing this by hand, use your PEMDAS. So start by doing the powers. 4 cube is 64, 4 squared is 16, then 4, and then 1. Now you do multiplications. 3 times 64 is 192. 3 times 16, that's 48. 3 times 4, that's 12. 2 times 1 is 2. And then finally, add up all of these numbers to get 254. So this number 1332 in base 4 represents the number 254. Now the next one is a little bit exciting because base 16 is a special base because since whenever we have a base, you can use the base 16 has 16 different symbols to use. So after the 9, they have letters such as A, B, C, D, E, and those letters, F is the last one. Those letters represent numbers. So B, for example, would be 11. And to decipher the number, start by writing the place values. So starting with the 1, and then 16, 16 squared, 16 cubed. And we only need the square because there's only 3 digits, so 3 place values, so starting with the 1. And now multiply each symbol or each digit by its place value. So 1 times 1, 5 times 16, and B times 16 squared. Now, as I mentioned, the symbols that you can use are 0, 1, 2, 3, 4, 5, all the way until 9. And then after 9, we have 10, which is represented with the symbol A, and 11, which is B. So I'm going to need to convert that B into 11 to multiply it by 16 squared. So 11 times 256, that's 2816, plus 5 times 16, that is 80, plus 1. So I add these 3 numbers, and my total sum is 2,897. Let's do another example. So now, how about converting a regular number, a Hindu Arabic number, into base 5? Well, if it's in base 5, my place values are going to be 1, 5, 5 squared, 5 cubed, 5 to the power 4, 5 to the power 5. Next, you might want to like simplify that. So 5 squared is 25, 5 cubed is 125, 5 to the power 4 is 625, and maybe the last one, 5 to the power 5 is 3,125. Now, notice that when we do this, we're looking for the highest place value that divides, that fits into the number. Notice that 3,125 is greater, so this does not fit into. So the largest value is actually 5 to the power 4, which is 625. So I start right there. I'm going to divide. I'm going to do kind of like the long division. Although I'm not writing all of the steps, this is kind of like the simplified way, which you can do with a calculator. Divide 1,844 by 625 if it's twice. And then in the calculator, you'll have like decimal points, like 2 point and a bunch of other things. We'll just write down the 2 and then multiply 625 times 2, which is 1250. Subtract, and that gives you your remainder. And then continue. Now I'm going to divide 594 by 125. And go on in that process if it's 4 times and the remainder is 94. Continue dividing until you get to the 1. You need all of the divisions, all of the place values. So 94 and now divided by 25. If it's 3 times, the remainder is 19. 19 divided by 5, the remainder is 4. And divide that 4. Notice that I'm using the remainders to continue dividing. Divide 4 by 1. If it's 4 times, the remainder is 0. So the easy way to remember this is you gotta divide by all of the powers or all of the place values smaller than the first one that you picked, or you gotta divide until the remainder is 0. But you gotta have all of the divisions in there. Even when the number is smaller, you still put it there as a 0, because since this is place value, if one of these powers were not to fit into it, we put a 0, and then we still represent the division. Well, as before, the answer is going to be found by using the quotients, the numbers on the top, 2, 4, 3, 3, and 4. And that's actually my answer. So 1,844 in base 5 is represented as 2, 4, 3, 3, 4. And then I put a 5 writing. Well, probably the last part that would be included on the test, or one of those parts, is doing arithmetic in different bases. And by these, we mean arithmetic usually refers to the operations such as addition, subtraction, multiplication, division. So we'll do a quick review, and that is it. So the first example says, find the sum in the same base as the given numerals. So the first thing is you're doing this by hand. There's no shortcut. You cannot use your calculator you can use it like in between, but you still have to like do this kind of like the old-fashioned way. So this would be start by writing your numbers in vertical order. And then you want to like match the place values from the right. So the units gotta match the well, because this is base 7, the next one would be like 7s, and then 7 squares, and then 7 cubic. Notice that this number has only 3 digits, so I leave kind of like a space or a gap in there. Because this is in base 7, our final answer, or all of any of the numbers that we use to do this operation, can only be digits less than 7. So that would be 0, 1, 2, 3, 4, 5, 6. Any number greater than this, or any digit greater than this, cannot be used during the process or to get the final answer. So I start by adding the units. 5 plus 4, this is 9, but 9 is greater than 6. So I need to write it in base 7. Well, because 9 is actually 7 times 1 plus 2, then these two numbers represent 9 in base 7. So 9 in base 7 is 1, 2, because I need 1, 7 plus 2 units. 7 plus 2 is 9. And just like in the old way, I put the 2, which is the place of the units, I place it right there, and I carry the 1 onto the next place value. So I put a little plus 1 on the top. And then I go back and add again the digits. 1 plus 2 plus 3, which is 6. And because 6 is still a number, a digit that is allowed in base 7, then 6 is just 6. No need to convert it. So I place it right below the column. And then I move on to the next place value. Now I'm going to add 6 plus 6, which is 12. This is bigger than 6, so I need to convert it in base 7. And since I can write the 7 fits ones, so 7 times 1 plus 5 is 12. So that means the 1 and the 5 actually gives me 12 in base 7. So once again, I take the number 5, the rightmost number, I place it in that column under the 6s, and then I carry the 1 onto the next place value. And finally, I add 1 plus 5, which is 6. And of course, this is like before, this is a digit that I can write in base 7, so that's just a 6. And that is my answer. There's nothing else to add to the left, so I've added all of my numbers. So 5625 in base 7 plus 634 in base 7 equals 6562 in base 7. Again, I don't call them like 5600 because they don't represent those numbers when you change it into regular base. They're actually smaller. Okay, let's move on to another example. So that was the sum. We also learned to do subtractions, and it pretty much follows the same format. Start by putting them in vertical alignment, so 434 in base 6 minus 241 in base 6. And then my digits are going to be 0, 1, 2, 3, 4. And because I'm in base 6, the largest digit that I can use is 5. And I subtract, starting on the rightmost column, 4 minus 1, that's a 3. That's an allowable digit, so I put it right under that column. Then I move on to the next column, which is 3 minus 4. But of course, this would give me negative. Like, if we cannot take away 4 things if you only have 3. So in those cases, we got to borrow. But since we're in a different base, so I'm going to scratch out the 4. I'm going to borrow 1 of these place values. There's 4. But because we are in base 6, that's adding 6 more to the 3. So 6 plus 3 now is going to be 9, and then minus 4. That's something that is going to be, I'm going to be able to subtract it because now 9 is greater than 4. But this 4 now becomes a 3. So on the next operation, I'm going to use 3 instead of the 4. Okay, well, as mentioned, 6 plus 3 is 9, minus 4 is 5, and then I place the 5 in the middle column. And last, 3 minus 2, that is 1. So my answer is 153. So if I subtract these two numbers in base 6, I get 153. Okay, let me move on to the next one. Multiplication. Again, to multiply numbers in different bases, we're going to do it like the old days. So you set up your multiplication. Typically, we put the number with the largest digits, the one that has the most amount of digits on the top, and the lowest amount of digits on the bottom. You could switch it, but it's just a little bit easier if you do it that way. And you start by multiplying. So then each of the digits on the bottom have to multiply each of the digits on the top, starting on the rightmost, so starting on the 2. 4 times 2 is 8. But remember, this is base 5, so I cannot use the 8. So I need to convert it into base 5. Well, since the 5 fits ones, you need 5 plus 3. Then 8 in base 5 is written as 1, 3. And so I write down the 3, the 1 on the units, and I carry the 1 onto the next place value. This 1 is going to be added. So I put that plus 1. So now I'm going to multiply 4 times 3, which is 12, plus 1. So that one so that addition, I'm going to do it after multiplying. This gives me 13. And then I got to convert it into base 5, which is equivalent to 2, 3, because I need 2 5s plus a 3. So 2, 3 it represents 13 in base 5. So I write down the 3 again on the next column, the next column to the left, and then I carry the 2 to be added to the next place value, so plus 2. Multiply again, 4 times 1, that is 4, plus 2 is 6. And since I am in base 5, I got to write it in base 5. So 6 in base 5 is actually 1, 1 because I need a 5 and a 1. And I write down the 1 on that specific column on the third one, and I carry the other one, the one in yellow, to be added onto the next place value. And the last multiplication is 4 times 4, which is 16 plus 1, 17, and then convert it into base 5. That's going to be 3, 2, because we need 3 5s and a 2 in order to get 17. And so I could do the same thing where I write down the 2 on the fourth column and carry the 3. But of course, there's nothing else to add. So I could just write down that, or some people call it the final carry, the last carry. You just bring down that 3. It's not added to anything else or multiplied to anything else. So my final answer is going to be 3, 2, 1, 3, 3, base 5. Okay, last, I have a multiplication example. So if I want to divide 332 in base 4 by 2, I would do it the same way, doing the long division process. And the first thing that I do is I take inside as many digits as I have outside. Since my 2 is only 1 digit, I would separate the first digit. So you always start by matching the amount of digits. And then you ask, how many times does 2 fits into 3? Well, that only 1, of course. And that's why I had that 1 on the top. So that 1 in yellow is the one that goes on the top. And then this 1, it's going to be the remainder. But the way that we do the entire steps would be by multiplying 2 times 1 and then subtracting from 3. And that will give you 1. Okay? So actually, these two, the one on the left is the quotient, and the one in green is the remainder. Now you bring down the next digit to get a 13. And of course, you ask the same question. How many times that 2 fits into 13? Now, I probably said this wrong because this is actually not specifically 13 since I am in base 4. So to find out how many times the 2 fits into this number, which is in a different base, we look at the multiplications. For example, 2 times 2 is 4, but in base 4, the 4 is written as 1, 0. 2 times 3 is 6, but in base 4, that is 1, 2, because you need a 4 and 2 to get 6. And notice that I'm still a little bit below. 1, 2 is slightly less than 1, 3. It's 1 unit less. So I'm going to do one more just to be sure. So 2 times 4 is 8, which in base 4 is 2, 0. Well, that's already too big because I have a 2 on the place of the 4s. So the largest number that fits would be 3 times. And that gives me 1, 2. So I put that 3 on the top. And then I multiply 2 times 3, which gives me 6, which is 1, 2. So I subtract the 1, 2. And of course, 3 minus 2 is going to be 1, and the 1's cancel, so that gives me a 0. So next, I bring down the next place value. So the 0 on the left does not count, so just focus on 1, 2. But this is exactly what we had before. We know that 2 times 3 is 1, 2. So we know that these 2 fits 3 times, and it gives you 1, 2. So I put a 3 on the top, multiply, and subtract the 1, 2. So finally, I got a 0. So this was a nice division in the sense that the 2 actually fits evenly into this number. So my remainder is 0, but in general, you could have any remainder as long as it's a number less than 4. So you could have, oh, well, maybe as long as it's a number less than 2. So we also could have a remainder of 1. Not 4, but 2. And that was my final example. So this is just to like mention the solution is the number that is on the top. But when you get a remainder, you're supposed to specify it. So I didn't put a remainder, but if I had had maybe a 1, I would say the answer is 133 plus remainder 1. Okay, this is all for today. Good luck with your exam and have a great Friday.
Thank you so much, Mr. Tintos, for presenting. Thank you so much, Mr. Tintos, for presenting today, and thank you all for coming. Thank you all for coming and being such a wonderful audience, and we definitely would like. We hope to see you again soon. So join us next. No, not next week. The week after Easter. I was going to say spring break. And look at the flyer I'm sharing right now. You'll see that for April 10th, we'll be covering for Math 1332 measurement, basic concepts of Euclidean geometry. Hopefully I said it okay. And for Math 12, and for Math, we'll be covering binomials and counting principles. Hope to see you then, guys. Thank you so much, and happy Easter to all. Have an amazing weekend. Bye. Thank you. Bye, everyone.
Thank you, everyone. Happy Easter.
Bye, everyone. Have a great weekend and also a happy Easter.
Bye-bye.
Bye-bye, everyone. Have a good weekend.